thanks for the organizer inviting me. So this is a talk with Itai. Where is Itai? Yeah, Itai is somewhere, should be here. I am sure that many of you have read or at least are aware of this very nice book of George Poya, if you want, the How to Solve It. Yeah, so actually I much prefer the Hungarian title. The Hungarian title is The School of Thinking or something like this. And the more I see the new word coming, more I think that maybe that's the only school will survive. So we will have still school for thinking. What else? I don't know. So anyway, this book is about how to solve problems. By the way, the first problem at the end is, that there is this bear goes 1 mile actually to the south, 1 mile to the east, 1 mile to the north, and ends up in the same point. And question is, what's the color of the bear? And so I'm not saying all this because of the bear, but because Poya not just give advices on how to solve problems, but also what to do when you can't solve a problem. And one of the basic advice, if you can't solve a problem, then solve another problem. So Itai is, working on quantum PCP for, I don't know, 20 years, maybe more, and he would like to solve it, can't. And then, we are good friends, close to the office, each other. So we often talk, he pushes me, let's solve together, we try, we can't. At some point I told Itai, why don't we solve another problem? Oh, sure, what? So for example, 2 plus 2. So we thought about it, we could solve it, we were very happy, but then somehow the happiness went away because we realized that this was not much really related to the quantum PCP. And so a few days later, Itai came back and he said that I have another simpler problem. And so what I will try to do today is to explain to you what was Itai's other simpler problem, how we solved it. And basically, I have two specific tasks to convince you about this specific fact. One is that what we solved is simpler than the quantum PCP conjecture, and I am sure you will be convinced of that. Now, the other thing is that this problem has a little bit more relationship with quantum PCP than 2 plus 2. I am not sure I will succeed about that, but you will see. Okay, so let's start with the basics. So we are kind of comparing constraint satisfaction problems and Hamiltonians, if you want, quantum Hamiltonians. Itai likes to call the classical problems classical Hamiltonians. So in the classical case, our objects are strings over some alphabet, and what we have local constraints. Every time a string violates the local constraints, we get a penalty. And what we like to do is to minimize these penalties, find the best string which has the least violation, least number of violation. In the quantum context, we have quantum states. We have Hamiltonian consisting of local terms, like the local constraints. Well, the violation here is the energy of the state, and we would like to find the ground energy or compute the ground energy, the minimum possible violation energy of a quantum state. So there are similarities and differences between the classical and the quantum context. So the similarities here, just a few of them. We have the Cook-Levin theorem 3 sat is NP complete. We have Kutaev theorem that K-local Hamiltonian is QMA complete. We can go down on the locality up to 2 if we are careful. So for example, max 2 sat is still NP complete, 2 local Hamiltonian, still QMA complete. But around 2, we have to be careful because we can go out of the hard domain. For example, 2 sat is in P, and if we have a frustration-free Hamiltonian deciding if it is or not. So I mean, if this is the question, then it's also in P. 2 dimension and the problems, both problems remain if the constraints are in 2 dimensions, still hard, and so on and so on. But there are also important differences. So for a starter, the Kitaev proof is arguably very different from the Cook-Levin proof. Just in one sentence, by the Cook-Levin proof, somehow you have this circuit computation, and you can, where every time you have some state of the circuit, and you can check this with local constraint, time by time, step by step. Kitaev is not doing that. He uses the clock construction, and this is a kind of global state with globally checks, and so the number of qubits he uses doesn't depend on the length of the circuit, and so on and so on. The k-local Hamiltonian is a promise problem, k-sat is not. I don't think it's an essential difference, but it is one. Now, in one dimension, it turns out that, for example, 3-sat or k-sat becomes easy. You can solve it, for example, dynamic programming, but the one-dimensional k-local Hamiltonian is still hard. Scott mentioned yesterday, we have search to decision reduction for CSPs.
Yeah. Miklos, in Kitaev's proof, the number of qubits does depend on the size of the circuit, right?
Size, not the time, not the depth of the circuit. So what I said.
Well, I mean, the size of the clock register will depend.
But that's constant, yeah. Register.
Not the number of qubits in the clock.
No, the number of.
I mean, the number you have to check in any one constraint is constant.
Okay.
Anyway.
So anyway, yeah. And of course, the biggest difference is that we have a theorem for classical case, and we don't have it for the quantum scenario. So what is the classical PCP theorem and what is the quantum PCP conjecture? So we have usually two formulations for the classical. One is this robust form of NP that you can have this fantastic holographic proof, which are short and randomly can just check a few constant number of places to find out if it's a correct proof or not. And maybe more relevant for this talk, the hardness of approximation variance for constraint satisfaction problem. So I have here, so again, H is a constraint satisfaction or classical k-local Hamiltonian, some bound on the constraints. And the following is hard, that I tell you that it's either, oops, I guess that's the laser. So either it's below some value, say 0, if it's a constraint satisfaction problem, or the best what you can get is at least some fraction of m, the number of constraints, and you have to decide that which case is true. So this problem, it's an easier problem than when you have a very small gap, is still NP hard. Okay. So linear proof just in 1 second. So in a very, very high level, you start with some say constant gap, and then you kind of double the gap in logarithmic number of steps, and you can keep, if every gap amplification step is quite complex, but you can come back to the original parameters, and finally you can end up with a huge gap. So what is the quantum PCP conjecture? So the quantum PCP conjecture says something similar. Now I have a Hamiltonian, a quantum Hamiltonian with some bound on the individual terms. And again, I guarantee you by a promise that I promise you that the ground energy is either below A or above B, where the gap between A and B is proportional to the size of the problem. And then deciding that what is the case is QME hard. Okay. So I'm coming back in just the same slide, except the last sentence. So if you want to say in one line that why this difference in the status of the problems, why we can't solve it, then maybe the one sentence reason is that while the classical scenario has the solution has a simple tensor-product structure, in the quantum case, we lack this. So in the classical scenario, the solution is just a string, obviously a tensor-product, while the quantum scenario, it's a quantum state where we have correlations. In the classical case, the local marginals determine the state, whereas in the classical quantum scenario, you can have several states with the same local marginals. Actually, it's even hard to determine if there is a state for a given local marginals which is consistent. They have the non-cloning theorem. So all this is somehow comes back to this lack of tensor product structure for the solutions. Just a small example. So for example, in Dinur's proof, we do something like it's called usually degree reduction. So if you have this graph with some constraint and say this, whatever are the constraint, this is a satisfying assignment. Then if I want to reduce this degree, in general, k, it's 5 to small degree, then I kind of can replace this sum here in the graph by an expander graph, same number of vertices as the degree. I connect every vertex from the expander graph just to one of the neighboring vertex here, and then I replace the constraint. So the new constraint inside the expander graphs will be just equality constraints. And then if this was satisfying here, I put the same value for all the vertices in expander, and that works fine. Now, just to do this step, what would be the constraints, the Hamiltonian, what would be the solution? You can try many things, you get into trouble. So what is the idea? I am just trying to define what we are doing. The idea is that we would like to make a parameterized problem. The parameter would be some integer k between 0 and n, in a way that when this parameter is 0, we get back the classical CSP. When the parameter is n, we get the quantum Hamiltonians. And for some constant k, we get something which is still a classical problem, but looks like much more the quantum Hamiltonian than the standard classical CSPs. And looks like much more is really what I mean is that we don't want this tensor product structure. So the best thing is to do is, instead of looking for a single assignment, we would like to have a distribution of assignments. So we want to define a problem where we are looking for distribution. So if I have a classical Hamiltonian, any distribution it satisfies or not, if I have a distribution on the assignments, so let mu be a distribution of an assignment, then I can look at the expectation of this Hamiltonian, and instead of looking for the best assignment, I can look for the best distribution from some set of distributions for which this expectation is minimal. Okay, so the basic idea is somehow going from assignments to distribution of assignment. Now, of course, I don't want to go to any distribution of assignments. That would be not a reasonable thing to do. So I would like to define a subset of distributions among all distributions, which again reflects somehow this quantum situation, still remains NP. So the way to do that technically is we go this. It's called the seek POVMs.
Sorry, Miklos.
Yeah.
So, of course, in the classical case, also you could have looked at a distribution, but there you always have an extremal point, which
yes, exactly. So I want to avoid that. That exactly. So the classical all distributions, it's a polytope. So I have the extrema are the optima, and I am back to the original things. That's what I want to avoid. So I want something. So I want a subset, a convex subset, but don't have the extrema are non-delta distributions. Exactly. I think I have a slide in this. Yeah, but that's the main point. Exactly. So let's take a POVM, so just a bunch of positive sum-weighted operators which sum up to 1. And once I have, in the normal quantum scenario, this gives a kind of mapping from states, this is now rho is a normal quantum states to probability distributions, where for any possible alpha in the POVM operators, the probability alpha is just the trace of rho times E alpha. Now, such a POVM is information theoretically complete if this map is invertible. And this is equivalent to say that this E alpha span the space of operators. So they are, if I am d-dimensional Hilbert space, they are d-square independent among them. And the symmetric property means that these d-square elements, so first of all, they are very simple positive operators, just projectors or proportionality projectors, so one-dimensional projectors. And And I want the symmetric, meaning that the inner product is the same. Now, it turns out that if you have these two properties, then the constant which I have here has to be 1 over d or whatever. But you have to remember that the important thing is that the inner product is the same and it's not 0. They cannot be orthogonal. Now, once you have such a P of EM, then we can define our objects, the k-local. I don't know if it's quasi-quantum or quasi-quantum. I hesitate between the two. So I Googled it yesterday. The Google says quasi-quantum. So what we will do, we fix. So we have to fix one specific P of EM for 1 qubit. So let this be, so then I have 4 of them because 2 squared is 4. And the symmetric property means that on the Bloch sphere, they form a regular tetrahedron. So for example, I can choose one of them, one of these projectors, just the 0, the cat 0, projector to cat 0, and the other 3, are somewhere below the equator, reasonably below that, make it a regular tetrahedron, and they have this 120 degrees among them. Okay, so these are the 4 operators E0 up to A3, and you can check them that they are satisfying the properties. That's by the regularity. And now the definition of the k-local quasi-quantum state is the following. So the first thing it says the obvious thing, so that it's a Hermitian and trace 1 operator. The second thing is, so if I would like to define a normal quantum states, then I should say that it's a positive definite operator. Now, instead of that, I am requiring global positivity only with respect to this specific sig P of EM. So what I'm asking for, that for every alpha among the indices of the P of EM, the trace of x times E alpha is non-negative. Now, these two guarantees that this mapping, which maps quasi-quantum state to the probabilities, is a mapping which is a probability distribution. So the mu alphas will sum up. They are positive by this property, and by this they sum up to 1. And now comes the funniest property. So this is kind of, it makes sense. If I would stop here, I would just get all probability distributions, and then we would have the problem Umesh just pointed out. And the last property says that if I'm looking at, let me call this k marginals. So what I mean is that I fix any subset of indices of size k. K is some constant. And I trace out all the rest. So then I am getting an operator on k qubit, and I ask that this operator is positive semi-definite. So if I'm just looking at locally k bits, then I can't distinguish a quasi-quantum state from a quantum state. But if I'm bigger than k, then of course I can get into trouble. Is this clear? That's the definition. So that's the object we are. And that's a definition. You kind of, you might like it, might not like it, but arguably we are, yeah, okay, so maybe let me see further that what are we getting. So I can characterize, going back to this distribution picture, so what kind of distributions, probably distributions getting. For this, the most practical thing is to, for a mathematical characterization, to look at what we call the dual basis. So the dual basis is just, again, a basis of the linear operators. Here is, it's a very simple definition. That's how you get from the E alphas, the D alphas. And so yeah, they are also spanning the space. They have also this operator trace 1. The big difference is that they don't have, they are not positive semi-definite. The E's are, they are measurements. And the point why we are defining is this co-orthogonality property, that the D alpha and the so if alpha is different from beta, if I take two different basis elements from D and E, then they are orthogonal. So the Schmidt-Hilbert inner product is 0. Okay? And so this property kind of makes this transition between quasi-quantum state and distributions very, very simple. So what I'm saying is that if I have a quasi-quantum state, as I defined previous page, and then I'm making the distribution over the alphas, the indices of the sigma basis by the tracing out operator, then what I get, this distribution is such that if I am writing up the state of the D basis with respect to these coefficients, the mu, the distribution, then I'm getting back the original state. And it's an if and only if. So that is the way to go from state, quasi-quantum state to, if you want, quasi-quantum distributions. And the equivalent definition via distributions, if you want, we could say that a state, just a probabilistic combination of the D alphas, is a k-local quasi-quantum state. If you look at the marginals of this k marginals of the distribution, you are making up the corresponding marginals of the quasi-quantum state, and what you get is null positive operator. Okay? So these are two equivalent parameterizations, and that's what I guess Umesh was referring to, that if you have a real quantum state, then you get some kind of distribution, of course, not all of them. Here are all possible distributions. You have these points which are just classical. CS, the distributions are deltas, and we are somewhere in between. It's a convex set of quasi-quantum distributions. And now the problem we are facing is the k-local Hamiltonian problem for quasi-quantum states. So here I have a Hamiltonian where I would like to find, if you want, I will call this the ground state, where I am minimizing over all possible quasi-quantum state instead of all quantum states. And the corresponding k-local quasi-quantum Hamiltonian problem is that I promise you that there is a serious gap between A and B. Either this ground energy is below A or above B, and we would like to decide which one is the case. And so the main result we have is this quasi-quantum PCP theorem, that this problem is NP complete. So again, this is a classical problem. It's NP complete. Well, you have to be careful in the sense that these things are not too fault-tolerant object, the quasi-quantum state. So we prove it for k equal 3. It doesn't mean that I have it for k equal 4 or 2. So that's the theorem, not less, not more. And the gap can be very small to very big. Okay. So any questions at this point? Yeah.
So I guess you have two in the theorem. You have like two different things you're using k for, right? Because k is like
very good remark. So the k which we are so we have the Hamiltonian, the locality k, and the quasi-quantum state we define the positive the same k. Now, if you are asking me, could it be it could, then you get different problems. Arguably the k for the quasi-quantum positive semi-definiteness should be at least as big as the k in the local Hamiltonian. But mathematically, you can completely thanks. It's a very important remark. Yeah. Okay. So NP complete, two parts. It's in NP and then it's hard for NP. And in NP is not totally trivial, but much easier. So think about it that we have a state which is a solution. Now, a priori, it can have a huge support, exponential size. So I guess at some point I forget to say I just defined all these operators for 1 qubit. So the way to go to n qubit is I do tensor product. And therefore, you know, in n qubit, I have 4 to the n operators. That's a big number. And so the way out is this, it basically goes back to an idea of paper of Pitowski, where he speaks about correlation polytopes and looks complexity questions about them, is basically to say that so we speak about now quasi-quantum distributions, and the theorem is that for every such distribution, we have a sister distribution. So the sister distribution has two properties. One is that obviously I need that the marginals are the same, and the other thing is which helps me is that the support of the sister distribution is small meaning polynomial. You know, if locality is k, then it's order of n to the k. Once I have these, then it's kind of trivial, the MP easiness, because instead of the solution, I give you a sister distribution, and I can specify this, you know, with a polynomial number of parameters, and then you can compute the marginals and check everything polynomial time. So why is this existence is true? And so this is you see that all distributions are in this polytope where I have 4 to the n, you know, delta distributions, and any of the distributions can be mapped to the k marginals. So how many k marginals I have? So I have n choose k, and then maybe for each element I have, you know, 4 possibilities. So I can specify 4 marginals by something like n choose k times 4 to the k, say n to the k parameters. And then, so the punchline is that we can invoke Kara-Theodoris theorem. So what does it say? It does say that in the plane you have 10 million points, and someone is in the convex hole, then actually there's a triangle such that 3 points out of this 10 million, such that this given point is in the convex hole inside the triangle. In the d dimension, you have always d plus 1 point. Okay, so here concretely it does means that I have, you know, n choose k plus 1 point, such that I already specify this distribution, and that's exactly the sister distribution. Okay, so it really goes back to this very nice Kara-Theodori lemma. Okay, so that's the MP easiness. Now, how about MP hardness? So, you know, you start and then you kind of come up with 2 obvious possibilities. So one is that I encode the hard problem as a classical Hamiltonian and computational basis, and as I will try to show, then the completeness is trivial, but soundness is hard. And another approach that I look at this Hamiltonian in this SIG-P of EM basis. And then we have the opposite situation. The soundness will be trivial to show, but completeness is hard. And then, you know, you have to do something else or message one of these approaches. So let's see the first one. So what I mean is that, I mean, this is the classical thing. So I have, say, a 3-set formula. I can always write a Hamiltonian. You know, the first clause is not satisfied. The only assignment which doesn't satisfy it is the 0, 0, 1. So I can, you know, penalize these assignments by writing down the projector and summing up these whole things. Of course, if there is a satisfying assignment for this original formula, then the corresponding quasi-quantum state has 0 violation, and that's perfect. So the completeness is easy. But what's happening if there is no satisfying assignment for here? So the problem is that, strangely, you still might have a quasi-quantum state which doesn't violate anything. And it's a little bit easier to see for an easier problem than 3-SAT. So let's just think about, two-coloring. So I want to two-color a graph. So my colors are 0 and 1. So let's say I want to two-color the triangle, which is a little bit hard to do. So what are the Hamiltonians for this two-coloring? So I want to penalize if you put here on every edge. So say on this edge, if I put here 0, 0, or 1, 1. So that's the projector which does that. And so the Hamiltonian is just the sum of these two, sum of projectors for the 3 edges. And the funny thing is that if you look at this following state, so 1/2 of the projectors to vectors with 2 1s minus the projector on 1, 1, 1, then first of all, it is a quasi-quantum state. So you can check it. As it turns out, it's too hard to compute. The 2 local marginals are all this 0, 1 plus 0, 1 projector plus 1, 0 projector. So the 2 local marginals are positive. And on the top of it, these 2 local marginals clearly don't violate any of the constraints. You see? So I started with a graph which was not colorable, and I still could come up with a quasi-quantum state which had 0 violation. Okay? So that's the problem with this approach. Now the second approach is, that's the easiest to explain if I start with a 4-coloring problem. And then I want to map this to the Hamiltonian on the E alpha basis. So the way to do this is that, for every edge, again, I want to penalize if the colors at the 2 endpoints are the same. So what I will do is that for every edge, sum up for all possible, collisions. So the E0, 0, E1, 1, and so on, the 4 possibilities. So this is the Hamiltonian, which is incidentally, I think it's called the antiferromagnetic Heisenberg Hamiltonian, if you like these things, maybe some shifting and so. So it's an interesting Hamiltonian. And now it's easy to say that if, any single D alpha, so any coloring, you take any assignment alpha, the corresponding D alpha, if this graph is non-colorable, then will violate something, so we will have some penalty, the number of violations, therefore any distribution will have that. So that's fine, but the completeness is broken. So what do I mean by that? So now let's suppose that the graph is 4-colorable. So there is an assignment, say this alpha star, which is doing the perfect 4-coloring. Then what you would like to have is that, you define the corresponding single, point distribution, D alpha star. And it's, of course, it's fine that the energy is 0, but it's not locally positive. As we have seen, any of these on just 1 qubit, the D alpha has a negative eigenvalue. And therefore, it's not a legal quasi-quantum state. So we choose to use this approach. So in the rest of the talk, I am trying to convince you that we can massage this idea and make the problem, the 4-coloring problem, a little bit different, and the Hamiltonian a little bit different, such that this basic issue will be addressed, that we will be able to come up solutions which are locally positive. Okay. So the basic thing is that you see this problem. I have this -1 here. So and I have, you remember this, there are 4 of them. So you have to mix them. You have to come up with many colorings. So somehow you have to kill this -1, of course, which is what I'm saying is now complete, non-mathematics. This 2 is better than 1. So I have some force here, kind of you could feel, and I will instantiate that if I have many solutions and I am making the convex combination of these solutions, then I have some chance to kill the negative eigenvalue. So how can I make many solutions? So if I have at least one solution, one coloring by this, so I am now for these 4 coloring problems, then obviously I can make from one solution 24 because I can permute all the colors. It doesn't change anything. So that's the kind of symmetrized version of this solution. And this already solves a little bit my problem because, so now if I look at the one marginals, so just on one qubit, then since I symmetrize it, it will be something like the sum of this d alpha, and the sum of this one individual d alpha has negative eigenvalue, but the sum of them, it's actually the identity or proportional to the identity. So that's already fine. So for one marginals, I am fine. But of course, I am not fine for 2 marginals. So if you compute it, it's not too hard to compute, but it's important for the rest to remember that for a given solution, I symmetrize it, and I am looking at the 2 marginals, meaning that I'm looking in particular points where I have the same color, of course, it's not a non-edge. If it's an edge, and of course I cannot have the same color because that's a solution. But if between non-edges, if 2 points ij don't form an edge, then of course I will have same colors. Then the corresponding 2 marginals, if you compute it, is the identity minus actually the projection to the singlet state. And again, this has then obviously one. Actually, it has. So it's not a positive matrix. Okay. So how can I? What can I do? So this quasi-quantum state, they are closed on their convex combinations. It's a convex set. So one simple idea is that I can pad it with the maximally entangled state. So the everywhere one matrix, and of course this will help me. So for example, if I take for some constant epsilon 1 minus epsilon times the maximally entangled state plus epsilon times my symmetrized solution, then it's kind of obvious that if epsilon is smaller and smaller, then I get a bunch of positivity from here. So it will be fine. I will end up with local marginals which are positive. But of course, what is wrong is that this penalizes everything, and therefore I will end up with global energy which is proportional to the number of edges, and that kills the gap. And therefore we somehow have to bring back this very high energy we got because of the maximally entangled state to some small range where the original gap is surviving. And so that's the scapegoat mechanism. So the scapegoat mechanism goes back to, either to the Torah or to the Pentateuch, depending on which way you read the book. Actually, it turns out that apparently the scapegoat is all over the Near East, back to the 3rd millennia was an important notion. So somehow, when the people, the nation, the group had some sins, and you wanted to get rid of the sins, then the way to do it was to actually concretely taking 2 goats. One of them was the scapegoat, the other was a goat which had to be sacrificed. But the scapegoat kind of get all the sins of the people, were chased out to the desert, and then everything was fine. So that's what we are trying to do. We violate this coloring constraint, a bunch of them. But we will take a scapegoat. We will take a new qubit. a scapegoat qubit. And then all this violation will be put on this poor goat, on this poor goat qubit. And then, in one qubit, you cannot get that much problems. So more precisely, I am having for every edge this Hamiltonian, which is the sum of the E alpha, for the 4 possibilities. And this is a 2 local constraint. Now I am extending this to a 3 local constraint, so that's how we will get the 3. And in this last qubit, the 3rd qubit, that will be the scapegoat qubit. And you can think about it that the scapegoat can be either in an active state and in a passive state. So the active state is anything which is not D0, and the passive state is a D0. And now you will get a penalty here only if you violate the edge, of course, so it's a bad coloring, but also if the scapegoat is inactive. If the scapegoat is active, then you see no problem here. This constraint is satisfied. Okay? So, and then, for soundness, I also have to have this scapegoat Hamiltonian, which penalizes if the scapegoat is inactive. And so think about it. Whatever you have, you will get a penalty at least 1, whatever state you have, because if you are in the inactive state, then okay, am I saying this right? If I am in the active state, sorry, I said it wrong. So this is if I am in the active state, then so any of these states, then this is 0, 1 minus 0 is 1, so I get a 1 penalty here. And if the graph is not colorable, then I will also get a penalty 1, at least 1 here, when the scapegoat is active. Okay, so if there is no coloring, then my penalty is at least 1. But if there is a coloring, then I can make up this state, which I was talking to you in the previous pages, the 1 minus epsilon times the max, the maximally entangled state, and the epsilon times this solution, symmetrized solution, now extended with the scapegoats. And while from here I will still get the 1 minus epsilon penalty here. When I have the solution, so X is a solution, when the scapegoat is active, okay, I am not saying this well. So I have a solution. So this is a solution. If this is a solution, then even if the scapegoat is inactive, I won't get penalty here. Therefore, I only get penalty for this term when the scapegoat is active, and then I will get a penalty at most 1 minus epsilon. So there will be a gap. Okay? So this is fine, which is not fine that everything I did is that I wanted local positivity, and this is still not locally positive. So things are getting a little bit complicated, and I probably should get higher level. So the way we are getting out is that we initiate a new scapegoat system. It's the 3 scapegoats. So 1 scapegoat is not enough. So the point is that if you have 3 scapegoats, so maybe let me come back here. So you see the problem, you see that it is not locally positive, is the following. So kind of imagine that you fix 2 original vertices in the graph and the scapegoat. Now, if you measure the scapegoat, on 3, if it were 3 positive, locally positive, then just measuring 3 bits, I shouldn't remark that something is wrong, that it's not a quantum state. It should behave as a quantum state. Now, let's suppose that I measure the scapegoat and they end up with having 0. Then what remains is exactly this symmetrized solution where I argued that this is, you see, having a negative eigenvalue. So that's the problem. So what I would like to have that even if I measure a 0, I have some more meat here. I should kill the negativity. And this more meat is coming from the 3 scapegoat. So the 3 scapegoats means that I will start with a graph, and this is a classical reduction from the just standard 4-coloring problem for another 4-coloring problem where the graph has a specific structure. And the specific structure is that the graph can be decomposed into 4 subgraph. It's 3 subgraph, 3. So I have a 3 partition of the edges. I have all the edges of my graph, and I can partition into 3 set of edges. These are the 3 graphs, such that these 3 graphs have simple structure, whatever it is, think about 3 loops, something like this. And the point is that for these simple graphs, I can have very good coloring solutions. The very good coloring solution means that I can have a distribution, a coloring distribution over all. Everybody in the distribution is a coloring, it's symmetrized. And the point is that any 2 local marginal is not just positive semi-definite, but it has an eigenvalue which is strictly positive. So, if you can have this, then you kind of, maybe you feel that then it's what's happening. So this is the 3 scapegoat Hamiltonian. So basically, these are my 3 graphs, the E1, E2, A3. Each of them has 1 scapegoat. And then, I penalize when all of the scapegoats are inactive. And the important thing is that the gap goes through like similarly, but if in this situation you measure one of the scapegoat, let's say the first one, then of course you will end up the problematic things. So this symmetrized solution which has negative local marginals, but you also end up with some part of this good solution. And the good solution can counterbalance. Okay, I don't see anything mathematics here. All this comes down to we have to make up combinatorially for these so-called simple graphs a bunch of solutions, so basically random assignments over which are colorings, which are symmetrized. And it turns out mathematically that the important parameter is the collision probability. So we want to show that any non-edge over these distributions, the probability of having a collision in colors is strictly bigger than 0. It's, comes out. So that's basically the combinatorial part. Okay. So what did we do? So we introduced this k-local quasi-quantized states, kind of generalized CSPs to distribution of assignments for assignments. So what we had, these distributions are relaxation of proper quantum state. Therefore, the ground energy is something smaller than for the quantum states. We proved the PCP theorems for quasi-quantum state, and I don't know, maybe so what I could say here is that, if you try to do the Iritz proof, this gap amplification in the quasi-quantum scenario, then this is hard because, you go out, the alphabet size increasing, then increases the locality, and, going out the locality here, you get into horrible troubles. But somehow what we suggest that we still can do this amplification cycle by going out from the quasi-quantum state. So kind of imagine that I have this quasi-quantum state, I do the inverse of the reduction I showed you, end up with this classical coloring CSP, then I can do the amplification, and then I'm coming back with the reduction. So this a little bit suggests that maybe something similar could be done or can be tried for the real thing, the quantum quantum scenario. So the idea is that maybe you cannot stay inside the quantum state. Maybe you have to try to go some other field and work there and come back. So, these are already just philosophical considerations. So open questions, basically everything. Well, did I convince you that this is better than 2 + 2? So all these other things I characterize classical cases. How about 1D systems? Is there search to decision? Can we use this numerical tool, lower one? Maybe we can disprove the quantum PCP theorem. If it turns out that this gap between the quasi-quantum ground energy and the quantum is so small that you can approximate them, maybe you can do it in NP. And if you fall in love with quasi-quantum states, can you have a computational model for them? Whatever you want. Okay, that's it.
We have questions, yeah.
What are the colors of the 3 scapegoats?
Sorry, what are the?
What are the colors of the 3 scapegoats?
Oh, so I said that they are, I just have 2 states, they're active or passive. So they are not coloring anymore.
But if you were to color goats, how would you color them?
0 or 1, 0 or, so 0 is the passive and 1 or 2 and 3 is the active. So I kind of, yeah, so it's the same. It's just, everything is the same on the same Ds, 0, 1, 2, 4, but conceptually the 1, 2, 3 is meaning that they are active, but syntactically it's 4. Yeah.
Yes.
Can you comment a bit on how the hardness depends on the K you ask for in the marginals? So 2, 3, 4.
So mathematically what I'm asking that or 3 marginals. So if the 3 marginals are positive, then the 2 and the 1. Okay, so I'm asking for the 3 marginals. What is the question exactly?
But if you ask for 2 or 4.
So again, that would be a different problem. So if I would define the K-local, so my quasi-quantum state where I acquire, 55 marginals positivity, that would be a different problem.
But 2. If I ask for 2.
I don't know what is, if there a result or, it's, again, try to say it's very unstable. So that's the result I have, and I have to, I really don't know if it's 2 or 4. I suspect, but it doesn't think, so this theorem doesn't say that.
Any other questions? Yes.
So is it the last question you said about the computational model for quasi-quantum
Yeah.
states?
Wow, Anurag, you made it. Impressive.
I see you said it.
Okay, so what about it?
The computational model for quasi-quantum state?
Yeah.
What do you mean by that?
Yeah, circuits or are they, can you do computation? So is it?
Is there a gate that you can define which?
Yeah, really, is there such a thing as quasi-quantum computation? I mean,
Any more questions? Okay, if not, let's thank Miklos again for a nice talk. And we have a 30-minute coffee break.